Hello friends, here in this video we will see a problem on protected type of flange coupling, and for that purpose here we have a question. Design a cast iron flange coupling for a mild steel shaft transmitting 90 kilowatts at 250 rpm. The allowable stress, that is shear stress, in the shaft is 40 megapascal and the angle of twist is not to exceed 1 degree in a length of 20 diameters. So length is given in the form of diameter. The allowable shear stress for coupling bolts is 30 megapascal. Now what is this protected type flange coupling? To understand it better, here I have the diagram. This diagram shows protected type flange coupling. It is here. Now, this coupling consists of two parts. One is the left portion, left half, other is the right half portion. In the left portion, we have a shaft which is connected to this portion which is called as the hub with the help of key. Next, this portion, it is called as the flange. On the right hand side also, here we have shaft which is connected to hub with the help of key, and this outer portion, it is called as flange, and here we have bolts. Now why it is called as protected type flange coupling? The reason for it is that in this coupling, instead of having thickness of flange as TF, we have another thickness called as T suffix P, which is called as the thickness of protective flange or protective cover. Now this TP value is provided in order to cover the bolt heads and the nut. As we can see here, the bolts head and nuts, they are completely covered. They are behind this thickness. So anyone who is operating near this protected type of flange coupling, then he would not get injured by the bolt heads. At the same time, any cloth or material would not be, you can say, entangled in this bolt head or nuts. So for that purpose we provide this protective cover. Now we have to design this coupling, and when we mean design, we have to start with the shaft. That is, here I'll say that we have to design the shafts. Next we have to design the hub, then we have to design this key. Next we have to design the thickness of flange on both the sides. So I can say that here we have flange. Then we have to design this protective cover. It is called as the protective cover, and at last we have to design these bolts. That is, we have to determine the diameter of the bolts. So these are the components which we have to design in case of protected type flange coupling. Now whatever was given in this question, I will write that in the form of data. So in the data, the first thing which I have to mention is the type of coupling. Here I'll say that the type of coupling is protected type flange coupling. So it is a protected type flange coupling here. Next, the question is, design a cast iron flange coupling for a mild steel shaft transmitting 90 kilowatts. This is the power which is given at 250 rpm, that is speed. So power P is equal to 90 kilowatts. So it is 90 into 10 raised to 3 watts, and speed capital N, that is equal to 250 rpm. Next, the allowable stress, which is shear stress in the shaft, is 40 megapascal. So tau is 40 megapascal, that is 40 Newton per mm square. This shear stress is for shaft. Then, and angle of twist is not to exceed 1 degree. So angle of twist is theta, it is 1 degree given, so it means it is pi by 180 radians. Then in a length of 20 diameters, length of shaft capital L, I'll say that is equal to 20 into D, that is the shaft diameter. Next, allowable shear stress for coupling bolts is 30 megapascal. So tau is 30 megapascal. This is for bolts. So here we have the data. Now let us get started with the design. So in solution, I'll write down step number 1. It is the design of shaft. Design of shaft. Now, as we see in this problem, there are two conditions given. First, shear stress for shaft is given, then angle of twist is given. So we have to calculate the shaft diameter by using two criteria. One is called as strength criteria and the other one is rigidity criteria. So I'll say that in design of shaft, first of all, since power transmitted by shaft is given by power P is equal to 2 pi nt upon 60. Now, therefore, T, it will be equal to P into 60 divided by 2 pi n. Power is given in the question as 90 into 10 raised to 3 watts into 60 divided by 2 pi into n. Speed is 250 rpm. So from this I will get the value of torque and my answer is 3440 Newton meter, or it is 3440 into 10 raised to 3 Newton millimeters. Now after getting the torque, we can start with the designing by using strength criteria first. So I'll say that first, by strength criteria, since torque transmitted by shaft is given by. Now for a solid shaft, since here the type of shaft is not given, we would consider it as a solid shaft. So for that, the torque formula is pi by 16 d cube into tau. So now, once we have torque, here I am considering the shaft as a solid section. This is the cross section of the shaft having outer diameter as d. Now, here I will put all the values. Therefore, torque we have got it as 3440 into 10 raised to 3 Newton mm is equal to pi by 16 d cube into tau. Tau is the shear stress for shaft, and in the problem it is given that for the shaft shear stress is 40 megapascal. So into 40, therefore I will keep d cube on one side, shift all terms on the other side. So at first I'll get the answer of d cube. Now if I take the cube root of that, first my answer of cube is 0.438 into 10 raised to 6. Next I'll take the cube root of this answer, and finally d value will be, therefore capital D comes out to be, my answer is 76 mm. This I will keep it as equation number 1. So here in this first step we have considered the strength criteria and got the diameter of shaft. Now I'll take the rigidity criteria. So by rigidity criteria, in that we have T by J, that is torque transmitted upon polar moment of inertia, is equal to G theta by L. This is the rigidity criteria. So now therefore T, it is 3440 into 10 raised to 3 Newton millimeter. J is the polar moment of inertia, and for solid shaft it is pi by 32 d raised to 4 is equal to, G value is not given in the question, so I'll assume G as 84 into 10 raised to 3 Newton per millimeter square, multiplied by theta is given as 1 degree, so it is pi by 80 radian, because theta we have to keep it in terms of radian. Next, the length of shaft is given in the form of diameter, that is it is 20 times of d. Now from both the side, as we can see, d and d gets cancelled, so here I have d cube. So after this what I'll get, I'll write it down. Therefore I'll shift d cube on one side, shift all the terms on the other side. So d cube, I'll get my answer as 0.476 into 10 raised to 6. Now this is the cube root, okay, cube of d. After taking the cube root, my answer comes out to be 78 mm. So now if we compare equation 1, in that the diameter was 76 mm by using strength criteria. In equation 2, by rigidity criteria, the diameter is 78 mm. So out of the two values we have to select the maximum value. So next I'll say that, therefore from equation number 1 and 2, selecting the maximum value as the diameter of shaft. So therefore D is equal to, by rigidity criteria the maximum value is 78. Now see here, when the answer is 78 mm, it lies in the range of 70 to 80 mm, because for the shaft the diameters are in form of step. So from 60 mm to 110 mm, the steps are of 10-10. So if our answer lies, it is 78, so it lies between 70 to 80. So we have to select the next higher value, and that is 80 mm. So instead of 78 mm, we will take 80 mm as the diameter of shaft. Next, this completes our step number 1. In step 2, in step number 2 we have design of hub. Now what is hub? Hub is a hollow portion like this. Now I'll say that for a hub I will denote its outer diameter as capital D1. Its inner diameter is nothing but the diameter of shaft, which is capital D. So hub is used to connect the shaft and the coupling. I can show it on the diagram here. As we can see, this is a hub inside which we have a shaft and which is connected with the help of key. So hub is like a hollow shaft, and for that we would be fixing the dimensions. I'll say that let capital D1, that is the diameter of hub, be equal to twice of the diameter of shaft. So therefore the diameter of shaft was 80. So finally hub diameter comes out to be 160 mm. Now after getting the hub diameter, as we can see from the diagram here, hub also has some length, and that length we can approximately take it as equal to the length of shaft, and I can calculate it. Therefore I'll say that length of hub, that is L, is equal to 1.5 times of D1 or 1.5 times of D. Actually this is the diameter of shaft. So here we have 1.5 into the diameter of shaft is 80. So length of hub comes out to be 120 millimeters. So now when we have designed the hub, that is we have got its outer diameter and length, I can say that considering hub as a hollow shaft subjected to shear, because there are chances that when the shaft is rotating, this hub, it can shear off, it can break. So now we can consider it in shear, and for that I can write down, therefore torque transmitted by hub T, it is equal to pi by 16, its outer diameter is to 4 minus inner diameter is to 4 upon its outer diameter into shear stress for hub. Now this is the formula. So now here from this equation we can get the shear stress for hub, and before that I'll say that assuming the flange and hub to be made up of cast iron having shear stress of 14 megapascal. See here I have assumed the material, that the material for hub and the flange, that is cast iron, mostly the material used is cast iron. Now I'll calculate the value of shear stress from this equation and check it with 14 megapascal. So I'll say that this is equation number A for us, and therefore put all values in equation A. So therefore Torque, it was 3440 into 10 raised to 3 is equal to pi by 16. Capital D1, that we have got it as 160, capital D, that is 80 upon 160 into tau. So throughout I have only one unknown, that is tau, and if I calculate, I'll get my answer of tau as 4.56 Newton per mm square. So this is the shear stress which is there in the hub, and as we can see it is less than 14. So therefore shear stress in the hub is less than shear stress permissible, which is equal to 14 megapascal. So therefore we can say that hub is safe under shear. So this completes our step number 2. Next we have step number 3. In that we would be designing the key. So step number 3 talks about design of key. Now for the design of key, as we can see, key is the member which is there in the shaft. Up till now in step 1 we have designed the shaft, in step 2 it was hub. Now in step number 3 we are designing the key. I'll say that for the design of key, since selecting key dimensions for 80 mm diameter shaft, as here I am selecting the dimensions. If the shaft diameter is 80 mm, for that the width of key W is taken as 25 mm and the thickness of key is taken as 14 mm. These are available from standard table for key dimensions. That this value I have got from the standard table. Now after this we can check the key in case of shear. So I'll say that therefore considering key under shear, so the torque transmitted will be equal to, shearing area is W into L multiplied by shear stress into the radius of shaft. Here I will denote it by capital D. Now how this shearing area will look like, that I will draw it here. That once the key has been sheared, it will look something like this. The key will shear into two parts and this will be the shearing area. And the shearing area is nothing but width of key into the length of key. This is length and here we have the width of key. So in this way we are getting the shearing area. Now I'll put the values. Therefore torque is 3440 into 10 raised to 3, width is 25 and the length of key can be taken as equal to the length of hub. Length of hub was 120 into shear stress is what we want to check. Diameter of shaft was 80 divided by 2. So from this I will get shear stress. My answer is, it is 28.7 Newton per mm square. So again the shear stress which we have for key, it is less, Mostly the shaft and key, they are made up of same material, that is mild steel, and whatever the shear stress value is there for the shaft, same will be there for the key. So I'll say that therefore shear stress for key is less than shear stress permissible, and the permissible value was given in the question as 40 Newton per mm square for the shaft. So 28.7 is the less value. Therefore I'll say that key is safe under shear. Now with this we complete the step number 3. Next, after this we have step number 4, that is design of flange. Now in design of flange, first of all I'll fix the dimensions, that is, since here we are having one outer diameter of the flange, so I'll say that let capital D3 be the outer diameter of flange, and let this D3 be equal to 4 times of the diameter of shaft. So therefore I will get the value as 4 into 80. So it means the outer diameter of the flange is 320 millimeters. Next I'll say that let TF be the thickness of flange, and let this TF be equal to 0.5 times the diameter of shaft. So final TF will be 0.5 into 80. So therefore TF comes out to be 40 mm. Next, thickness of the protective cover, because it is there in protected type of flange coupling, this TP, this thickness, therefore thickness of protective flange, that is T suffix P, will be equal to 0.25 times of the diameter of shaft. So therefore TP is equal to 0.25 times of 80. So now thickness of protective flange, that comes out to be 20 millimeters. Next, after these fixing the dimensions, here as we can see, when the shaft rotates, hub will rotate along with it, and there are chances of the hub to break the flange. It can shear it off in like this, up till here it can shear it off, that is this portion would get removed. So that is called as shearing of flange. So I'll say that considering shearing failure of flange, I'll write down, since shearing area capital A, that will be equal to pi into D1, that is the diameter of flange, multiplied by the thickness of flange, because as the shearing area is the circumference of the hub multiplied by the thickness of flange. Therefore shearing strength of flange is given by T is equal to pi D1 into TF, that is the area, multiplied by shear stress tau into, now since we are considering it for the flange, and flange will fail at the junction of hub, so here we have diameter of hub divided by 2. So from this we can check the value of shear stress. So I'll say that, therefore I'll go on putting the values. Torque was 3440 into 10 raised to 3 is equal to pi into d1, it was 160. Thickness of flange we have got it as 40 into shear stress is what we have to check, multiplied by d1, again it is 160 divided by 2. So from this I will get shear stress. My answer is 2.14 Newton per mm square. Now we can compare this. I can say that since shear stress for flange, which is 2.14 Newton per mm square, this is the shear stress which is there in the flange. Now this value is less than shear stress permissible. For the flange, I have assumed the material as cast iron, and for that the shear stress is 14 megapascal. So here our value is less, so I'll say that therefore flange is safe under shear. So here in step number 4 we have completed the design of flange. Now the last part in this design, that is step number 5, that is the design of bolts. Now as we can see in this diagram, bolts are connected. Suppose what happens is the right hand side shaft, it starts rotating, but the left portion is stationary, it has not started rotating. So the right portion rotates, left portion is stationary. Because of that, the bolts, they can break into two halves like this, it can shear it off. One portion is moving, other is stationary, so that results in shear. So the bolts are failing under shear, and for that here we have center to center distance between the bolt, which is called as pitch circle diameter. So I'll say that in design of bolts, let D2 be the pitch circle diameter for bolts, and that is assumed as it is 3 times of the diameter of shaft. So therefore D2 will be equal to 3 into 80, and that is 240 mm. Now I'll say that considering bolts under shear, now when the bolts are shearing, they would be breaking in this form. Here I can just explain it with a 3D diagram. Here I have just drawn a diagram so that I can explain the shearing failure of bolts. Now this bolt, it can shear off in two parts. Here we would be having another head, or here, since I'm considering the bolt, so it would be only up till here. This I'll just draw a broken section here. Now the shearing area is here for the bolts, and I can say that it is nothing but the cross section, and since the bolts, they are threaded, so the shearing area would be at core diameter. I'll say that considering bolts under shear, since shearing area is equal to pi by 4 into dc square, that is the cross section, therefore shearing strength of bolts, that will be, therefore T is equal to pi by 4 into dc square multiplied by number of bolts into area, that is then shear stress for bolts multiplied by pitch circle diameter divided by 2. So here I'll say that let n, that is number of bolts, be equal to 4. It can be greater than 4 also. So I'll put the values. Therefore torque was 3440 into 10 raised to 3 is equal to pi by 4 dc square into n multiplied by shear stress for bolts was given 30 in the problem, and the diameter of pitch circle, that is it was 240. So from this I will get the core diameter. Here this n is 4. So I will get the value of core diameter as the answer which I have calculated. It comes out to be, after taking the square root, it is 17.4 millimeters. So here I am getting the diameter for the bolt, which I can approximately take it as 18 mm. So now, as we have seen in this video, we have completely designed the protective flange coupling, starting with the shaft, then hub, flange, thickness of flange, protective cover and bolts, and with this we complete this design.